We're back. Welcome back. In this video, we're going to talk about applied statistics. You know, most of the time in the quant world, quant funds, hedge funds, however you want to classify different firms, banks, a lot of quant roles aren't actually concerned with your ability to conduct research or trade. Really, they just want to see that you have the capacity to answer a whole bunch of probability puzzles and games. That is, of course, you can figure stuff out on the fly in a fast-paced environment. Whether or not that's productive for screening candidates is beyond the scope of this video. I'm going to show you how we can apply some statistics to extract, say, a meaningful parameter for a particular unknown distribution. In this case, we're going to be looking at the population mean. We're going to use the law of large numbers and central limit theorem. And this is going to go beyond your business analytics class. This ain't your freshman year, sophomore year business analytics class at university. No. We're going to talk about what it means to simulate each of these draws from some unknown distribution. Then we're going to apply the central limit theorem. So if you're still watching, hang with me, and you're going to be ahead of the curve. If you're not interested, then, I don't know, go watch some of my other videos or buy my courses or something. Alright, so for starters, let's just quickly go ahead and import numpy as MP. We'll import scipy.stats as SCS. Import matplotlib.pyplot as PLT. Okay. Alright, so now what we're going to do is we are going to go ahead and use a standard uniform distribution as an example to talk about what's going on here. And then after that, we're going to apply the concept that I'm going to illustrate here, but in that case, I'm going to apply it to a different problem. Alright, so we're going to approximate a parameter. Alright, so let's go ahead and say that, I have D, and this is going to be a random vector. We're going to use a uniform distribution, and let's just go ahead and use a standard uniform distribution, okay? So this is going to create one draw from the standard uniform distribution, right? I can keep doing this. Each draw has equal probability, such it's a flat line, right? If we were to go ahead and draw the probability density function, it would just be a flat line. If we wanted to, we could even define it with LaTeX. I would say f of x is equal to, and then I would have, I'm not going to do the piecewise, I'm just going to do fraction. We're going to say this is 1 over beta minus alpha, right? So beta minus alpha. So it's parameterized by beta and alpha. X sin u alpha beta. And then that is going to be for any x that is going to be between alpha and beta. So I'll have less than or equal to x and then less than or equal to beta. Okay. And this is going to render just on frame so you can see it here. And then it's going to be 0 elsewise, anywhere else. Okay. This is a standard uniform distribution, so if we go ahead and we were to plug in 0 and 1, we would get 1, and that's for the entire case here. As it would turn out, right, the expectation, so FBB will do E of, let's say, x. This is going to be equal to alpha plus beta, right, and that's pretty simple. It's the start point plus the end point divided by 2. Okay, and that shouldn't be a surprise to anyone. If we have, equal probability of selecting a number between 0 and 1, we're just going to add the start, add the end, divide by 2. The variance we can get as the expectation of x squared minus the expectation of x squared. Okay, don't get that confused. It's E, then we have x here. Okay. I'm not going to go ahead and actually work this out. This is actually just going to be equal to, if we do it, we have 1/12 times beta minus alpha squared. Okay. Now, this is if we know the distribution, right? So we can go ahead and run this, and we can generate another draw, but we can also generate a series of draws, right? So I can generate 10 draws. It's going to be a vector of 10 from a standard uniform distribution here. Okay. Now, we know that the expectation is defined as such, and the variance is defined as such. But, you know, if we actually were in a practical situation, we wouldn't know the governing distribution here. Right? We actually wouldn't know that. So what I want to do is quickly illustrate how we can apply the idea of the law of large numbers central limit theorem to draw a conclusion about the population mean, and then we'll apply it to a problem where we can actually approximate the population mean. We draw some conclusions essentially. Okay. Alrighty. So for starters, we can go ahead and we can compute a sample average. Alright, so let's say I have 10 draws from a uniform distribution. I can create a sample average x bar. It's going to be np.mean_d. Then I can also create the sample variance. Alright, now the sample variance, right, if I was to go ahead and define this here, I would have bar x is equal to, and then we're going to have 1 over n times the summation from I equals 1 all the way to n. So in this case, n is going to be 10, right? Because we have 10 draws. All right. So that is the sample average. Okay. Then we can also compute the variance of such an estimator. That would be the variance of bar x. Okay. And this is where it gets kind of interesting. Okay, so we're actually taking this is what's called an estimator. Hopefully you've read my articles and watched my other videos. If you haven't, read and watch for clarification. This is something that should be implicit in your solutions at this point. But we can actually compute an expected value for such an estimator, and that expected, or not just the expected value, but the variance of the estimator. So in this case, what we're going to do is we're going to compute the expected value first. So that is going to be math BB. E of, we're going to have bar x, right? And what we can do is we can go ahead and apply this guy right here to this, and we need an xi here. We can go ahead and apply this to this guy here. Okay. So what I'm going to do is I'm going to throw this x bar into my expectation. So I will take this guy, plop him in there. This is equal to math BB E, right? We will take bar x, and instead of bar x, I'll paste that guy in there. And then by linearity of expectation, I can just go ahead and pass that expectation whoop, right on through to the xi. So I can copy this, paste this in here, and then I can go ahead and take this expectation, throw it on in here. And now what I can do, let me wrap this in parentheses to make it a little more clear, is I can apply what we know about this particular distribution here, right? So the expectation in this case is alpha plus beta over 2. Okay, so if I do that, then what we end up with is we end up with 1 over n times the expectation. So we end up with just the expectation of the random variable. Okay, this is what's called an unbiased estimator for the sample, or for the population mean, rather. And if this is a little fuzzy, I would definitely encourage you to check out my articles, but essentially what's going on here is this E of xi, since we know the governing distribution, we can just go ahead and plop in alpha plus beta over 2, and it is going to be IID, that is, each of these xi's in this sample average are drawn, or assumingly drawn, from the same distribution. So we're going to get n sample averages, essentially. And then we're going to divide by n, and we just end up with alpha plus beta. Or essentially, we get, I'll write out the extra step, 1 over n times n, and then we have that alpha plus beta over 2. Right? See? And then that goes away, and we're just left with the population mean right there. Okay? We can do the same exact thing for the variance of x bar. And as it turns out, what ends up happening is when we apply this variance to the sample mean, take this summation right here, we end up with this extra 1 over n. Okay, so I apply this variance here. I'm going to take out this 1 over n, and then we actually square it, right? Because whenever we take something out of variance, we square it. So frac, we get 1 over n squared. Then we still have n variances, right? Because it's a summation of IID random variables. So we have n times the variance of xi. So I guess if you wanted to be a little more specific here, this could just be replaced with any xi. So this could just be x1. And in the same context here, this is the same thing as e of x1 because it's IID. But in this case, we know the governing distribution, right? So we know the n cancels out here, and we also know the variance. So we end up with the fraction of, we have 1/12, right, times n, right, times, and that's going to be beta minus alpha squared. Okay, so that right there is going to be the variance for this particular distribution, the variance of the estimator for the sample, or for the population mean. All right, so that's all well and good, but how does this apply to what we're dealing with here, right? This is much simpler to interpret, so let's just go ahead and talk about what's actually kicking here, right? So when I create D, and I say D is a random draw from a uniform, we're drawing 10 random draws from the uniform distribution parameterized by 0 and 1, so the so-called standard uniform distribution, and we are taking the mean of that sample. So this is giving us the x bar. And what we're saying is we expect, essentially, this sample mean as n approaches infinity to approach the population parameter for the average, so the population average, in certainty. That is the law of large numbers. So probabilistically certain, that is. Okay. All right, now that's interesting, but how can we actually see that? Well, let's just go ahead and start by creating a sample of 1, and we will print x bar, right? Analytically, what should the mean be? Alpha plus beta over 2. So 0 plus 1 over 2 is 1/2. So it should be 0.5. So if I run this with one sample, we get 0.3, right? Now, this is what's interesting. If I was to increase this to 5, right, we get 0.33. Increase this to 10. I get 0.49, 100, 0.49, 1000, 0.50, right? And as we could see, as the sample increases arbitrarily, we are going to get the convergence to that population parameter. Okay, the wording in statistics can be very confusing, especially because sometimes there is bad notation, but in the context of this, we have an estimator, this sample average right here, and the expectation and the variance is going to be defined as such, right? So this is unbiased, and then this is going to be the sample variance, okay? And this is going to be the case, but the interesting thing here is it doesn't matter what the underlying distribution is. So in other words, here we have a uniform distribution, but this could be Poisson, this could be Bernoulli binomial, it could be normal, and this idea is still going to be the case. So if I was to change this, let's say to Poisson, right, and we parameterize Poisson with a lambda, let's make lambda 10, then it turns out if we were to do this entire step again, we would just end up with the expectation for the lambda distribution, which is just lambda. Okay, and the sample variance would be lambda over n. How can we see this? Well, let's just go ahead and do it, right? So we have Poisson, so the parameter is 10, and we're creating one draw. So what does the sample mean? Oh, 2 S's, Poisson. So we have 12, this is one draw, right? This is one state of the world, right? Another draw. So let's go ahead and do 5. That's 10, right? Right on the money right there. 10, 9.3, 100, 10.31, 1,000, 10,000. Hopefully you see my point here. It's converging to that population parameter, right? Now, we don't actually have to know what this is to construct this estimate. We can gather data regardless from the distribution that it comes from, and we can draw some statistical conclusions about that data, okay? This is where the central limit theorem comes into play, all right? This is the idea that the distribution of all of these x bars that we're creating here, all right? Now, assuming we have the same sample size, okay, across each sample, is going to be approximately normal. Then we can standardize and end up with a standard normal distribution. Ooh. Then we can compute some probabilities. This is an amazing result from statistics. We've talked about this a lot in prior articles, prior videos. But let's just go ahead and take a look at what this actually looks like, right? So the law large number says this is going to converge in probability to the population parameter as our sample size increases. Cool, we've seen that. How do we see the central limit theorem in action? Well, what we're going to do is essentially a Monte Carlo simulation. We're going to say x's, or I'll call this x bars, is just an empty list, for I in range. And let's just have n equal to, let's say, 10. Okay? And then we're going to do this simulation of 100 samples from a Poisson distribution. Again, the underlying distribution doesn't matter, but let's go back to this uniform case. So I'll say uniform, we'll say 0, 1, okay? And then instead of printing it, I'm going to do x bars dot append x bar. Now, let's go ahead and plot this distribution of x bars. Whoopsie, we don't want to plot, we want a histogram. Check that out. Okay, that doesn't look very normal, right? We're not really going to be approximating any probabilities here. Okay, what we need to do is we need to increase our sampling, our sample size, right? So we're going to take 100 samples, right? We're going to do this, okay, 100 times. All right, all right, all right. What about 1,000 times? Ooh, look at that. How about that, huh? Okay, so how does this, if we have 1 here, change the case, right? We need a reasonably large sample. Typically n is greater than 30, right? Because if I just sample 1, right, from a uniform distribution, I'm just going to get a uniform distribution. So if n is large enough, right, so let's say even 10. Look at this. How incredible is that, right? The sample mean, right, ends up being, the estimates end up being a normal distribution, okay? So if we have 1 draw from a uniform distribution, we take the mean, that's just the draw itself, add it to a list, take the histogram, we just get the original distribution. That ain't too handy, right? But if we have, let's say, a sample of 20, right? Check this out. This is starting to look normal, right? Increase this to 200. Hopefully this is just making it very clear. If we increase the bins too, this will look nicer. So let's make this 50. Let's make this 1,000, and then hist will do bins equals maybe 50. Does that look nice? Ooh, look at that. That's starting to look normal. Okay, maybe 30. Look at that. Look at that bell curve right there. All right, so that's what the central limit theorem is. That's the difference between the central limit theorem and the law of large numbers, okay? The central limit theorem is going to allow us to compute probabilities based on this distribution that occurs when we sample with n greater than 20 or 30-ish, and we resample, we're going to get something that looks like a normal distribution. But the center of that distribution, the law of large numbers, is going to say that center should approach the population parameter for the average. That's the key, okay? That is the key right there. Resampling like this isn't necessary all the time, right? As long as we increase the sample, we should eventually be centered around that particular population parameter, right? So if I have 50, right? If I have 50 and then I go out and I resample another 50, right? That's not going to change the probability in any sense, right? We know that the distribution is going to be normal. We're better off just using the 100 sample. Okay, hopefully that's clear. I know that can be a source of confusion. Like, why are we using 50? Like, why don't we just use 50 and then do another 50, do another 50, whatever, so on and so forth. You want to use the largest sample that you have to construct your X bar, because that is going to be the closest to the true parameter, the center, right? Okay, and we saw that, right? So we saw that when we get rid of this Monte Carlo-ish simulation here, and we have 50, right? Where's 50 centered around? It's pretty close to the 0.5 here. Let's start with 10 just to make it very clear, right? So this is around 0.4-ish, right? But if we were to increase this to 1,000 law large numbers style, this is going to be closer and closer to 0.5, right? So that right there is the logic in saying we don't want to just construct a whole bunch of X bars. We want the largest sample that we possibly have to construct this estimate, because then we could do something called hypothesis testing, okay? So let's go ahead and take a look at how we can bridge this gap between probability and statistics, applying this idea. Okay, so what I want to do is just create an example problem where we can use the central limit theorem to essentially approximate the probability of a team being on a certain side of a soccer field. Okay, so like essentially like on average, where do we expect one team to be on which side of the field? The way that I'm going to define this problem space, okay, again, we don't necessarily know the underlying distribution, but for the simulation example, I'm going to create one, okay? So what I'm going to do is I'm going to say two soccer teams, A and B, have the following distribution of play time on each side of the field, all right? And it remains to be seen if this is an effective way to construct such an idea, but this is going to be which side the ball is on. So which side of the field is the ball being played on? Is it going to be played on team A side or team B side, all right? So we're going to denote the center, okay, the center of such a field as 0.5, okay? So if you're less than 0.5, you're going to be on team A side. So if X is less than 0.5, the ball is being played on team A's side. If X is greater than 0.5, the ball is being played on team B's side. Okay, and I'm going to give you the distribution for this random variable. All right, let's assume that we have a whole bunch of intervals for where the ball is being played on either side of the team. We're going to sample some sort of frequency, right? We'll say like maybe every 5 minutes in the game we'll see, okay, where in relation is the ball to one side of the field to the other, right? So we'll have 0 all the way through 100, okay? So we'll say 100% is going to be on team B's side all the way, towards the end of the corner kick situation, and then 0 is going to be a corner kick on team A's side. All right, so assume we just resample every 5 minutes or so or something like that. All right, for simplicity's sake. All right, I'm going to say X is going to be distributed uniformly, and I'm going to say it's distributed 0,0.75. Okay, so there is a clear favorite. The ball is going to be played on one side of the field longer than another side of the field. All right, but we don't know this. All right, let's just assume that we are actually measuring where the ball is across the field, and we are going to sample this every 5 minutes, every time team A and B plays, and we are going to go ahead and take a look at where we can expect the ball to be most of the time, okay, using the central limit theorem. So if this is the case, right, then we know the expectation, we know the variance that we defined right here. All right, but I want to do the case where we don't know. I want to just use the sample. So what I'm going to do is I'm going to actually generate from this particular distribution 0 to 0.75, okay? And I'm going to generate, let's say we have 200 points, okay? So we have 200 points, right? If I was to display this on a histogram, we would only have 1 point, right? So I'm just going to go ahead and print X bar, right? So this right here is our sample average, okay? This is our sample average. This is our X bar. We're applying the sample average to this data, and we are receiving an estimate for the population average, all right? Now I'm going to pose a question, and we're going to answer it using the central limit theorem. What I want to ask is essentially, let's see, based on the data we have observed, is there sufficient evidence to suggest that the ball can be expected on team B's side more than team A's? Okay. So based on the data we have observed, and that is simulated from this distribution here, is there sufficient evidence to suggest the ball can be expected to be on team B's side more than team A's? Okay, so how do we go ahead and construct this sort of approximate probability here? Or essentially, how can we test this, this hypothesis? right? So that is statistical inference right there. We're making an inference about the population parameter that we do not know, right? Of course, since this is a simulation, we can get it right here, but what I want to do is I want to approximate it using the central limit theorem, okay? So what I'm going to do is, if you recall the fancy old equation, right, that is the central limit theorem. The central limit theorem says that if we have, right, the limit as n, right arrow, infinity, and we got to wrap this in some LaTeX here, right, of the probability of bar x minus mu, so this is the true population parameter, divided by, in this case, we have the sample standard deviation, so we're going to say S, divided by, divided by square root of n, okay? So if this is the case, right, so we have the sample standard deviation here, then we know this is going to go ahead and follow a t-distribution, all right? In other words, if I was to assign this variable, okay, let's say t is equal to, I'm going to wrap this in LaTeX again, right? I'm going to take this guy right here, paste it right here. This is distributed with a t-distribution, and then we are going to say with degrees of freedom, we have, let's see, n minus 1, okay? So this is an approximate distribution, all right? The particularly keen among you will notice that this will not be the case should we not have a sufficiently large n. Okay, and that's because this is not necessarily coming from a normal distribution. We have to assume that there's normal distribution in order to use a standard normal over chi-squared, but in this case we have a sample standard deviation out of population, so we are using a t-distribution kind of inappropriately. Okay, so for the sake of this example, what I want to do is I want to say that assume population variance is given by, and then we can just go ahead and use the population variance, okay? I will say sigma squared is equal to, and then we have to do that original equation of 1 over 12, and this is going to be times, right, beta minus alpha squared, so that's 0.75 squared, all right? And then we can just compute this very easily, right? So I would just say 0.75, whoopsie. Throw this in code. I will say that sigma is equal to mp dot square root, and this is for the, not the variance, but the standard deviation, right? And we are given the population variance. So I will say 0.75 squared divided by 12, okay? And that would be sigma there. As it turns out, right, if we were to compute, let's say, mp dot variance, right, or let's just use std of d, ddolf1, so that's the sample, we can see that that's pretty close, right? So this sin of not assuming an approximately, or a normally distributed variable, that is this time that is being spent on either side of the field, you know, this is really only a sin if we don't have a sufficiently large enough sample. We have 200 points here, right? It would be reasonable to approximate with a normal distribution instead. So instead of using a t-distribution, we can just go ahead and approximate with the normal distribution, even if we have this sample standard deviation here. So what I'm going to do is I'm going to say this is distributed approximately. So let's assume now that we don't have population variance, okay? And I'm going to say that this is approx. And instead of t, I'm going to use a standard normal. Okay. So instead of a t-stat, we got a z-stat. All right. It's reasonable to assume this is going to be approximately standard normal. All right. So then in this case, right, the formal central limit theorem is instead of s, we actually have a sigma here, and that is equivalent to cap phi of this entire side here. Where we have this being less than or equal to some constant, and then we just throw that constant in the cumulative distribution function. So this is the formal central limit theorem, but we can approximate the probability for the parameter here, that is the population mean, even with the sample standard deviation. Since we have such a large sample, it does turn out that the t-distribution converges to a normal distribution at infinity anyway, asymptotically. So this is not an insulting approximation at all. And depending on your margin of error, if your margin of error is something that you have to be particularly concerned with, it may not matter. And in this case, if you take a look at the x bar right here, if we have 0.5 as being the deciding factor, then really we can get away with this sort of cheat probability approximation. If this was closer, like 0.4, then maybe this approximation would be less appropriate. Okay, so let's go ahead and construct this z here, and we're going to do a hypothesis test. All right, so what I'm going to do is I'm going to say H0 is our null hypothesis, that is that mu is going to be equal to 50. Okay, the alternative hypothesis, H1, is going to be that mu is less than 50, I believe. So depending on what the question was, is there sufficient evidence to suggest that the ball can be expected on team B's side more than team A's? Really, it's not going to matter here because this is a symmetric case. You know, if we find evidence that it is less than, sorry, not 50, this would be 0.5. If we find evidence of mu being less than 0.5, then we would be able to answer this question all the same, right? And if we were to find evidence that it was greater than 0.5 or not greater than 0.5, we would once again find sufficient evidence, right? Because it's a binary case, that is, we would be able to discern whether or not it's on A or B's side. We can just flip this. I encourage you to do this the other way and see how the logic applies the exact same way. Okie dokie. So now what we have is a hypothesis test to conduct, all right? Really, we just got to construct this z-stat. All right, so what I'm going to do is I'm going to say z is equal to, we will take x bar, right? So that is going to be what? X bar minus mu, okay? And mu under the null hypothesis is 0.5, okay? So first we assume H0, because we don't actually have it, but let's assume that it's correct, okay? So we go ahead and we throw in mu here as 0.5. Then we're going to divide by the sample, standard deviation d/dBOF1 as a reasonable approximation, divided by the square root of n, which I believe is 200. Yes. Okay. So I go ahead and I throw this here, run this, and whoa, look at that number right there. You probably have no idea what this really is at all. Hopefully you do. And you're like, wow, look at that test statistic. That is ridiculous, right? Holy guacamole, right? Really, what we're going to do now is we're going to go ahead and talk about what this is, essentially. Okay? Let's go ahead and visualize a standard normal distribution. Okay? So I'm going to say S or Z is equal to np.random.normal 0, 1. We'll do 1,000 or 10,000 samples. plt.hist z. Okay. So what we're looking at here, right? We are essentially looking at the probability density that is a standard normal random variable. This is the probability density function for a standard normal random variable. Okay. So the probability of draws close to 0 are what? Pretty high, arbitrarily, right? Compared to draws out to -4. Okay? This is where all the intuition comes in. So if you made it this far, you're about to master this. I hope. Okay? We know, and we said right here, that approximately, if we demean and divide by the sample variance, square root of the sample variance, sorry, then we have something that is distributed approximately normally, right? If this is the case, then what we're going to do is we're going to pose this question. If the true population mean is 0.50, what is the probability, essentially, the probability of observing this sample? Okay, so we scroll on down here, right? Just look at this distribution. This is 0.4. There's almost no mass here. If we go all the way out to -7, it's going to be a puny number. In fact, we can actually compute that, right? To compute that, I would do scs.norm.cdf. Okay, and then in this CDF, I'm going to throw this z. Look at that probability. It's so close to 0. So what this probability is saying is this is the probability of observing the data that we've recorded from Team A and Team B's soccer games, okay? The probability of observing this data if the population parameter is 0.5. That is, they spend most of the time in between both sides of the field, okay? The probability of this being the case, that is the true parameter being 0.5, is puny. Absolutely puny, right? So essentially what we're going to say is we are going to say that this is not the case. We are going to reject the case that the population parameter is 0.5 in favor of the case that the population parameter is actually less than 0.5. Okay? And this is helpful, right? Why? Because now we can answer this question. Based on the data we observed, is there sufficient evidence to suggest that the ball can be expected on Team B's side more than Team A's, right? So if this is the case, right, then we would expect most of the game, and I believe we had this is greater than 0.5, right? We're going to be on Team B's side. We're saying absolutely not. We're saying most of the time we're going to be on Team A's side. We're going to be less than 0.5, right? So the ball is being played on Team A's side. We can answer this question based on the data we've observed, the approximate probability of observing this data, that is that the sample mean, essentially, or the population mean is equivalent to 0.5 is almost 0. Okay, so a better approximation, or a better estimate rather, for the population average is that it is greater than 0.5. So we would reject this null hypothesis in favor of this one. So that is that the population parameter is less than 0.5. In other words, long way of saying, we've essentially just statistically shown, and this is statistically, okay, we've statistically shown we can expect approximately most of the time that the ball will be played on the left side of the field rather than the right side of the field. And there's a million and one different ways we can use the central limit theorem to go ahead and approximate probabilities. This is just going to go ahead and be one of them, okay? Assuming that the expectation is a reasonable parameter, that is the population mean is a reasonable parameter to discern whether or not Team A or Team B, the ball's on Team A or Team B's side in the first place, okay? So hopefully this makes sense. This right here is the standard normal distribution, and really at the end of the day, all we're doing whenever we do some sort of hypothesis test is we are saying, hey, under this state of the world, where the true population parameter is 0.5, right? The true population parameter is 0.5. What is the probability of observing this data? And oh boy, is it tiny. Oh boy, is it tiny. This would be the p-value right here. Okay, and you can reject at a certain significance level, and there's a whole bunch of different interpretations. Go watch my video about the interpretations of confidence intervals, and you'll have a better idea of the interpretation in a frequency sense. But this is the formal idea here. Okay. Okie dokie. So you can even determine the magnitude in which we play more on Team A or Team B's side, right? So we can conduct another hypothesis test, and this is starting to get very close to bad science. You have to be particularly careful with how you construct this. But what if we get closer to the actual population mean? So we actually throw in 0.4 here, right? 0.4. We want to reject that it's less than, that it's actually less than 0.4. So we're testing if it's actually equal to 0.4. Then under the null hypothesis, instead of 0.5, we have 0.4. We run this. Look at that. Look at that. In this case, we actually fail to reject the null hypothesis. That is that there is enough probability, right? Because we are essentially, what? If we throw in, what is this z stat right here? -0.9, that's like right here. It's actually reasonable that we would observe the data in this context. So we failed to reject the null hypothesis here. Interesting. So we failed to reject the null hypothesis with this sample of 200 essentially points in time of teams playing and which side of the field they're playing on, we failed to reject in favor of mu being less than 0.4. But this is actually an error, right? I wonder if there's a way of quantifying this error. There is, type 1, type 2, and then this is essentially going to the idea of a confusion matrix. That is, you have a false positive, true positive, false negative, true negative. Okay, so this would be a false negative. Okay, and there's a way to quantify that probability, and the power of a test tells you the sample size required, okay, so this 200, to figure out the probability of essentially not making such an error. Okay, but we could talk about that in another video. Hopefully this is just clearing up the idea of a test statistic. Okay, that is, when we standardize it, we demean it, divide by the square root of the sample variance of the variance itself, whatever we're given. This is how we apply the essential limit theorem. In the context of the law of large numbers, it tells us that we would want this sample to be as large as possible. That's going to give us, essentially, you could think about it as the most accurate estimate toward the population mean. Okay. So I hope you enjoyed this applied statistics example. Once again, most firms are going to ask you questions that are, in similar vein to this, applying probability theory, statistics, seeing if you actually understand, these main ideas rather than, just if you can talk about finance. All right, cool. Hope you enjoy this. We'll talk about type 1, type 2 error in another video, maybe, if it is, of interest. Otherwise, thank you so much for watching. Go buy my courses. It helps me out tremendously. Other than that, I will see you in the next video. Thank you so much for watching.